All right, in this video, we're going to take a look at how to use similar triangles to solve a classic Calculus 1 related rate problem about shadows under streetlights. So let's jump right into it. A 6-foot tall man is walking at 3 feet per second past a streetlight which is 15 feet tall. How fast is the tip of his shadow moving 2 seconds after he passes under the light? All right, so our first key step on solving any related rate problem is to find the rates of change. And again, a lot of times we can find these by the units. Anytime you have a unit that's per a unit of time, like a feet per second, that is a rate of change that we're going to want to write down in a little bit. Okay, secondly, a related rate problem, the question itself is always a rate of change. So how fast the tip of a shadow is moving, okay, that is a rate of change that we're going to want to write as a derivative. Okay. Now, because this isn't things like widths or lengths where we could quickly assign a variable like W or L, what we want to do is draw a picture so that we can assign the variables right on the picture. Okay. So what I'm going to do is just draw a light. Okay. It doesn't have to be a fancy picture. Okay. So we have a street light. We have a man who walked past it. Okay. And then the street light's going to cast a light. It's going to hit the top of his head, go down to the ground, and that casts the tip of his shadow. All right. Now, when we're drawing this picture and we start to assign variables, we only want to put variables on things that are changing. So for example, his shadow is growing, so we would want to put an S there for shadow maybe. Okay. He's also walking away from the street lamp. Okay, so we're going to put another variable there. I'm going to just say x, okay, for the distance from the man to the streetlight. Okay, it also mentions that the streetlight is 15 feet tall, but that's not changing. The streetlight shouldn't be growing or shrinking in the middle of this problem, so I don't need a variable on that. Same thing with the man. He's 6 feet tall, okay, but he's not growing or shrinking in the middle of the problem either. So we can just label 6 feet. We don't want a variable on that either. Okay, so going back to the rates of change in the problem, it says that the man is walking at 3 feet per second. So that's how quickly x is changing, or dx dt is equal to 3 feet per second. It's asking us about how fast the shadow is moving. So it's asking us what is ds dt. So ds dt is question mark. Okay. Now it's actually not quite asking about that in this problem, which we'll see at the end of the problem, but we'll get to that again at the end. All right, but that's our first key step, is we want to find the rates of change in the problem, and that helps us do the second key step, which is to find an expression or an equation which relates together these variables x and s. All right, and on a shadow problem, the typical way to do this is with similar triangles. We'll notice that the man and his shadow is forming one triangle, and that's sitting inside of the triangle formed by the streetlight all the way to the tip of his shadow. Okay? Since they're sitting inside of each other, they're called similar triangles. So the sides are in proportion to each other. So for example, for the blue triangle with the man and a shadow, on the ground, S over the man's height, 6, is in the same proportion as the big red triangle. Well, along the ground is x plus s, and in place of the man's height, instead of that, on that side is 15. Okay, so this is an expression which relates together the two variables x and s. And one thing about these expressions is you can simplify before you take a derivative. So I can cross multiply here. So 15 times s will give us 15s. And then cross multiply the 6 over to the other side. 6 times x plus s gives us 6x plus 6s. And we can even further simplify it by putting all the s's on one side. So subtract 6s gives us 9s is equal to 6x. And if we wanted to, we could divide both sides by 3 in this particular problem. So 3s is equal to 2x. All right, so now that we have an equation relating together the two variables that are changing in this problem, we can take the derivative with respect to t. Now, again, all the derivatives are with respect to t, so when we take these derivatives, we're going to have to use our product rules, our chain rules, our quotient rules, and explicitly implicit differentiation. So when we take the derivative 3s, it's just 3, okay? But then we always have to tack on a ds dt or dx dt, the variable that we're taking the derivative of with respect to time. Okay. On the other side, the derivative 2x, I'm sure you know that, is just 2. But again, anytime we take the derivative of a variable, we need to tack on that implicit differentiation, like a chain rule, dx dt. Okay, so it's asking us what is ds dt, and we know what dx dt is. It's 3, so we can just plug that in, and we should be able to solve. Okay, so we got 3 ds dt is equal to 2 times dx dt is 3. Okay, so that means when we divide, ds dt will be equal to just 2 times 3 over 3, or 2 feet per second. Okay, so we solved this problem with similar triangles, and we got excited, and maybe we look in the back of the book and it's the wrong answer, or we type it in MyLab and it's the wrong answer. Okay, so what's going wrong with this is the fact that the shadow is moving because the man is moving as well. So you'll notice that this says that the shadow is moving at 2 feet per second, but the man is already moving at 3 feet per second. So somehow the shadow is moving slower than the man. That doesn't make any sense. The man and the shadow are attached. So actually, how fast the shadow is moving, we have to add these two things together, because the shadow is growing at 2 feet per second, plus it's moving at 3 feet per second because it's moving with the person that's casting the shadow. So we end up with a total of 5 feet per second. Okay, so overall, we did our 3 key steps. Again, we found the rates of change, and we wrote those as derivatives with respect to time. Then we found an equation or expression that related together these two variables, and then we took the derivative with respect to t, remembering to use implicit differentiation where necessary. We plugged in the given information, and we solved. Okay, as always, if you liked this video and it helped you, please like the video and subscribe to my channel.